As you see here, we're going to discuss, or I'm going to discuss, solving logarithmic equations. Of course, logarithmic equations are equations that have a variable involved in a logarithm, one or more, okay? And I got a little ahead of myself. I went ahead and stated the path that we take to do this. So this is kind of our guiding premise on how we're going to solve logarithmic equations. We're going to be given an equation that has logarithms in it. It may have one or it may have several. And if it has several logarithms in it, then what we try to accomplish generally, this is not exclusive, but for the problems that we'll be looking at, I think so. We want to get it to a form where we have the logarithm, one single logarithm, the logarithm of an expression, whatever our base is equal to a number. And when we get that form, then we can convert that to an exponential form and continue solving. So here's what I'm referring to. In this very first example, we're already at that stage. That is, we're given the logarithm, we're going to solve, okay? So we're trying to solve this. Solve the logarithm of 3x minus 2 base 2 equal to 3. Now see, this is already in that form. It's the logarithm of an expression, which is 3x minus 2. Our base a is a 2 in this case, and it's equal to the number 3. So to solve this, what we'll do next is convert to exponential form. And when we convert to exponential form, what I've said in the past is that we have our base 2 to a power 3 is equal to the argument, in this case 3x minus 2. Now I'm going to change, I wrote it over there on the right because now what I'm going to do, because we're going further in solving equations, I'm going to actually put my argument on the left side. So 3x minus 2 is equal to the base 2 raised to the power 3. That's the way I would handle that. And once we evaluate 2 to the third, this is a pretty simple, equation to solve. Is 3x minus 2 is equal to 8, and we can continue solving. And that's what I meant above. And now we continue solving. So we would add 2 to both sides, and we get 3x is equal to 10, and then we divide both sides by 3, and we'd get x is equal to 10 over 3, and we would most likely leave our answer in that form and not approximate any at all. Now, here is the problem, okay? This is pretty straightforward to do this, but we have to have a warning here. And the warning is that sometimes we create extraneous solutions. Sometimes we have extraneous solutions. An extraneous solution means the process of solving creates what we think is a solution, but it's not really a solution. And so we have to always check the feasibility of our solution. And here's what we have to remember. We've got the logarithm of expressions, but what we have to remember, is the logarithm, regardless of the base, we can never have the logarithm of 0. That's not allowed. And we can never have the logarithm of a negative number. That's not allowed. And so we have to take our solutions and make sure that it doesn't cause any argument to be 0 or negative. And so in the case here, we have x is equal to 10 thirds. And in our original equation, not our original equation, but in our original equation, we actually have this argument, don't we? And so what we're worried about is when we put that 10 thirds in for x, would that cause us to have the logarithm of 0 or a negative number? Well, we can check real quickly here that if we say 3 times 10 thirds and then minus the 2, which this is base 2, well, 3 times 10 thirds is 10, isn't it? And so this is going to be the logarithm of 10 minus 2, base 2, or the logarithm of 8, base 2. And that's okay. It's because 8 is a positive number. So that's what we're worried about. Now, Sometimes it will be an issue, other times it won't be an issue, but we have to be concerned about it. So the solution to this equation is 10/3, 10 over 3. And again, how did we do it? We had the logarithm of a single expression is equal to a number. And that's not always going to be the type of equation we have. Sometimes we'll have equations that have more than one logarithm in it, and that's the first part of the statement above. We're going to use laws of logarithms to gather the logarithms all to one side and combine them using the laws of logarithms into a single logarithm. That's the purpose, that's the point. Okay, here you can see that we're asked to solve the equation logarithm of x plus 3 base 6 is equal to 1 minus the logarithm of x plus 4 base 6. Now, before we get, I know that this is not the way you're going to think when you solve these problems. You're not going to think in advance, but let me do that for us, at least here. Whatever, for instance, we can't have a solution that is x equal to negative 7. Because if we put a negative 7 in for x, in the first logarithm would have the logarithm of negative 4, and in the second logarithm would have logarithm of negative 3. And in either of those cases, we've got a problem because we're not allowed to have the logarithm of a negative number. So we're going to have to be careful at the end to see what kind of solutions we get and to make sure they make sense in the original equation. But remember what we're supposed to do. We're supposed to gather the logarithms to one side when we have an equation that has more than one logarithm, and then combine them in a way so that we get a single logarithm. So let's start with this equation. The logarithm of x plus 3 base 6 is equal to 1 plus, minus the logarithm of, what is it, x plus 4 base 6. Now what I'm going to do is I'm going to add this logarithm to both sides so that I have a constant 1 on the right side and both of my logarithms on the left side. So after I do that, I'll have the logarithm of x plus 3 base 6 plus the logarithm that I'm adding to both sides, x plus 4 base 6. And of course that leaves only a 1 on the right-hand side. Now, my laws of logarithms say that when I'm adding two logarithms of the same base, it's important that they're both base 6. When I'm adding two logarithms together like that, I can actually create a single logarithm where I actually multiply the two arguments together to be my factors of the new argument. So I can change this into the logarithm of a new argument, which is an x plus 3, the first argument, times x plus 4, the second argument. Of course, it's base 6, and it's equal to 1. Now, we could do this now or later, but I suppose I'm going to do it now. The logarithm of that x plus 3 times x plus 4 is the same thing as x squared plus 7x plus 12. If we were to multiply that out, that's what we would have. Equal 1. Now, that's where we are. Remember what we were trying to accomplish. Get a single logarithm on one side equal to a constant on the other. And after we do that, then we convert to exponential form. And so the exponential form tells us that the argument, x squared plus 7x plus 12, is equal to the base to the power 1. Of course, that's just 6, isn't it? So as we recognize that we have nothing more here than a quadratic equation. And so what I'd probably do is to get 0 on the right side by subtracting 6 to the first, or just 6 from both sides. So that would give me x squared plus 7x, and a 12 minus 6 is a 6, isn't it? Equals 0. So now I've got a normal type of equation for me to solve, and I would try to solve this quadratic equation by the method of factoring. And I think if I can factor that left side, x plus 6 times x plus 1, I believe is the way it will factor. And so you recognize then the two solutions would be -6 and -1. Okay, now let's look up above. We're worried about what happens when we use an x equal -6. See, and I don't need to write down the whole equation, but look right here. If I put a -6 in for my x in the first logarithm, then I actually end up with the logarithm of a -3. And that's the problem. I can't have the logarithm of -3. So this -6 is an extraneous solution. Now, certainly a solution to this quadratic equation, but it's not a solution to our original equation. And so we have to throw out -6 as a solution. It won't work. Well, what about -1? Well, look above. The logarithm of x plus 3, -1 plus 3, oh, that's going to be the logarithm of 2. And that's okay. Now, on the other side of the equation, we have the logarithm of x plus 4, -1 plus 4, base 6. Well, that'd be the logarithm of 3, base 6, and that's okay. So -1 is, in fact, the correct answer. There's only one answer in this case, and it is the correct answer, and because it's feasible, it's reasonable. We can use it in the original equation in all logarithms. Now, many times you're going to have tutors or you're going to have people tell you, oh, if you can't have a negative value for a solution of a logarithmic equation. But you see here we can. What you can't have is a value of x that causes a negative logarithm in the original equation. That's what we have to be worried about. But just because the x value is negative doesn't mean it cannot be a solution. We see here that it is. Well, this next problem, it looks similar, doesn't it? But of course, it has some similarities, but it's different. Notice here, I'm not listing a base on the logarithms, so we interpret that to mean that we're talking about base 10. Okay. Well, remember the prescription for solving these normally is to gather our logarithms to one side. And so this time, I'm going to be subtracting the logarithm of x minus 3 from both sides. Anyway, I'll start out with my original equation. And, oops, I've got a 1 plus logarithm on the right side, but I don't want that extra logarithm on the right side. I want them all on one side. So I'm going to subtract logarithm of x minus 3 from both sides. When I do, then it will look like the logarithm of 2x minus the logarithm of x minus 3 is equal to 1. Now this time we're subtracting logarithms, and of course the way we do bring those together as a single logarithm is we actually have, that's law number 2, isn't it? We say, oh, well, that's the same as the logarithm of a fraction where the numerator is 2x and the denominator is the argument x minus 3. So that's the single logarithm that we're dealing with now. Now our base is 10. So we convert this, and when we do, we'll have our argument, which is a fraction, has to be equal to our base to the power 1. Now, it just so happens in both of these cases, I have a 1, but it could be a 2, it could be lots of things, couldn't it? But now I have an equation that is, and let's make that look a little better, as 2x over x minus 3 is equal to 10. We have a rational equation. The way we would normally solve that is that we would try to get rid of the denominator, and the easy way to do that in this case is multiply the fraction by x minus 3. But if we do that, we have to multiply on the other side as well by x minus 3. Of course, on the left side, we're left with 2x. On the right side, when we distribute, we've got 10x minus 30. And so we would, to solve this, probably the simplest thing to do is to subtract 10x on both sides. And we'd have negative 8x is equal to negative 30. And when we divide by -8, we'd have -30 over -8. And that's certainly positive, isn't it? Negative divided by negative. And 30 over 8, see, will that reduce? 2 will go into 30 15 times and into 8 4 times. I don't think it will simplify any further than that. Now, just because the fraction is positive, that doesn't mean we might have a positive x value that still can't be a solution. So what we're worried about is our two arguments. See, since we're taking a logarithm of 2x, we've got to make sure that 2x is positive for the x value we've chosen. And since we're taking the logarithm of x minus 3, we've got to make sure that x minus 3 is positive when we use the x solution that we got. So let's just check that out. 2 times x, and if our x is 15 over 4, well, certainly that's 30 over 4, and that's okay. That's positive, isn't it? Now, x minus 3 may be okay, but we don't really know, because if we take a number and subtract 3, we might get a negative result. So what we're going to have to do is decide what we really have here. And 15 over 4 minus 3, well, 3 could be written as 12 over 4. And you see that 15 minus 12, what is that, 3 over 4? So when we put a 15 over 4 in for our x on the right side, then we do get the logarithm of 3/4, which is a positive number, so it's okay. So now we're convinced that this is, in fact, the solution. But we have to be sure of that. Okay, there's a few more that I want to do, and I do want to show you an exception to what I have been doing. And it's something that we can use once in a while, but not all of the time. You can see here we have an equation, a logarithmic equation to solve. The logarithm of x squared plus x plus 1 base 5 is equal to the logarithm of 3x plus 4 base 5. Now, notice there's no constants. We just have two logarithms only. And that, in that case, we can use a different technique. We could go about solving this just as we have before. Okay, and I'll make a point of this. Is what I said before is that we want to gather our logarithms to one side. And so we could say that this is the logarithm of x squared plus x plus 1 base 5 minus the logarithm of 3x plus 4 base 5 is equal to 0. Now, if we did that, hold on just a moment. So if we did that, we would bring the two logarithms together by saying the logarithm of the fraction x squared plus x plus 1 divided by the argument 3x plus 4, and of course this is base 5, equals 0. Now when we convert that, we have the fraction x squared plus x plus 1 over 3x plus 4 is equal to 5 to the power 0. But 5 to the power 0 is really 1, isn't it? So now we have our fraction x squared plus x plus 1 divided by 3x plus 4 is equal to 1. And so we need to solve that. Well, to solve that, I'm going to come up here because I want this space at the end to show you a comparative way. So we would multiply both sides by 3x plus 4, wouldn't we? And if we did, I'm kind of skipping a step there showing that, we'd have only x squared plus x plus 1 on the left side, and when we multiply the right side by 3x plus 4, we'd end up with 3x plus 4. And then we would go about, we notice that this is a quadratic equation, so we would get 0 on the right side by subtracting 3x and subtracting 4 on both sides. And so then it would look like x squared minus 2x minus 3 equals 0. And can we factor that? It looks like it's an x minus 3 times an x plus 1. And so we get the solution x equal 3 and x equal -1, don't we? Now, are those valid solutions? Well, if we put a -1 in for x, I mean, certainly if we put a 3 in for x, if we look above, we have only plus signs, so 3 squared plus 3 plus 1 will be positive, and so will 3 times 3 plus 4 be positive. Just, I'm looking up here, okay? The -1 is the only thing I worry about, but if I put a -1 in there, I'm just going to have -3 plus 4, that's positive. And if I put a -1 in here, I'll have -1 squared, which is 1, and then I'll have -1 plus 1, so that will also be positive. Okay, that's everything. So both of those are good solutions. Okay, those are good solutions. Now, let me show you here a quicker way. And I wanted to see that what we've done would work. I don't like to look at exceptions and say, oh, you always need to, here's a new rule. Okay. But here we do have something different. We don't have any extra constants that are outside logarithms. So on the left-hand side, we have one logarithm, and it's equal to another logarithm we have on the right-hand side. And because the logarithm is a one-to-one function, and that may not mean much to you, but because the logarithm is a one-to-one function, that means if two logarithms are equal to each other, then what we're taking the logarithm of must be identical. So we could conclude right here that x squared plus x plus 1 must be the same as the argument we have over here, since the logarithm of each is the same. Now, we go immediately to an equation. Look up here. Look right here. Isn't that where we were after quite a bit of work? Okay. So you see that we've kind of passed through a lot of work that we don't have to do here. And I'm going to jump to the end. When we finally get this solved, we'd have 3 and -1. And when we checked, we realized that both of those were, in fact, solutions. And so we could have done this in a much quicker way in this particular case. In this particular case is we have logarithm equal to logarithm and nothing else involved, and the bases are the same. That was the critical issue here. Well, I want to look at a couple more that are a bit more challenging, but it's something that we need to know how to do. So we'll continue this on the next page. As you look at this problem, this looks not much different than anything else we've been doing, does it? It doesn't look very much different. So as we begin to solve this, it seems like we'll do pretty much the same thing. Okay. We'll rewrite the equation down here so we can start solving. So we're going to bring those two logarithms together, aren't we? Create a single logarithm, and then we'll convert. And so what we do is we multiply together the two arguments, don't we? Of course, this is base 8, and it's equal to 2. Now, I guess we could do this now or later. I just prefer to do it now. When we multiply the x plus 7 and the x plus 6 together, we'll get x squared plus 13x plus 42, I believe. I believe that's right. Double check me to make sure that I'm correct there. Okay, equal to, of course, base 8. So now when we do our conversion, we'll have this argument, x squared plus 13x plus 42 is equal to, in this case, 8 to the power 2, which of course is 64. Now, we're going to solve this quadratic equation, and so we need to subtract 64 on both sides. And when we do, we get x squared plus 13x minus 22, I believe, equals 0. And so there's the quadratic equation we need to solve. Now, we look at this, and we may think we can factor this. Okay, we may think we can, but I encourage you to double check. You know, the quick thing to try is an x times a negative 2, a 2 and an 11. So x plus 2 times x plus 11, but that'll give a plus 22 and a plus 13x. So we've got to have a difference of those, and we don't know how to factor this easily. Okay, this is not something we know how to do. So we have to use the quadratic formula to solve this. So remember how the quadratic formula goes? The solutions are given by the formula, the opposite of b plus or minus the square root of b squared minus 4 times a times c, and all that's divided by 2a. Okay? And of course the a is the coefficient of x squared, the b is the coefficient of x, and the c is the constant term. So in this case, the a is 1, the b is 13, and the c is negative 22. And so we begin by doing our substitutions. So the opposite of b, it's the opposite of 13, isn't it? Plus or minus the square root of b squared, 13 squared minus 4 times a, which is 1, times c, which is negative 22. All divided by 2 times a. Now, let's be clear about what this is. There are actually two solutions wrapped up in this. One when we use the plus, the other when we use the minus. So one of the proposed solutions is negative 13 plus the square root of. Now, rather than waste our time here, I'm going to tell you what we should get, and you can double check it. 13 squared is 169. And then we have a negative 4 times a positive 1 times a negative 22. So we have 169 plus 88. And when we add those together, we get positive 257. And that's not a perfect square, so we can't simplify that any further. Now, the other value of x we get would be when we use the subtraction sign. And so we'd have negative 13 minus the square root of 257 divided by 2. Now, the problem we're facing now is that we don't know if either one of these are valid values, because we don't know whether they would cause x plus 7 to be negative or x plus 6 to be negative, do we? So here's the next step we would take. We would get our calculator out and we would approximate the square root of 257. And so I'm going to actually round our entire answer to 3 decimal places. So I've used my calculator on calculating negative 13 plus square root of 257 over 2 and rounded to 3 decimal places, and I get 1.516. Now over here, on the other hand, I'm going to do the same thing. I'm going to use my calculator, and when I do this time, I get approximately negative 14.516. Now, look above, x plus 7, if x is 1.516, is positive. X plus 6 would also be positive. So this is a good solution, isn't it? That's the approximate value. This is the exact value. So we have the exact value, and it helps us to know what that approximately is. On the other hand, if x is negative 14 something, then x plus 7 is negative, and also x plus 6 is negative. And so this is not a good solution. It's an extraneous solution. So in this case, those would not be part of our solution. We would, as we've seen already, we would get approximately 1.516. Okay, the last logarithmic equation I want to solve is on the next page. And here it is. Doesn't look too much different until, oh, look here. Here we have a base 8, here we have a base 64. And the laws of logarithms only work if we're dealing with the same base. And so we've got a big problem here, is we can't bring those logarithms together as a single logarithm unless we have the same base. Now, we might consider this. Either change the first logarithm to a logarithm base 64 or the second logarithm to a logarithm base 8 by using the change of base formula. And I think we might have better luck if we try to reduce the base. So I'm going to use the change of base formula for the log of x base 64, and I want to change that into base 8. So that means I create a fraction where I'm going to have base 8 logarithms. What do? I take the numerator is going to be the logarithm of the original argument, but of course base 8 we're dealing with now. And the denominator is going to be the logarithm of the original base using the new base that we're converting to. So we can replace log x base 64 with a fraction that involves log 8. Now, also look here though. The logarithm of 64 base 8, what power do we put on 8 to get 64? We put a power of 2. So this is really the logarithm of x base 8 divided by 2, which we could in fact even write as 1/2 times the logarithm of x base 8. So we take our original equation and we replace log x base 64 with a 1/2 log x base 8 equal 1. So now we can bring those two, well, not quite. I started to say we can bring those two logarithms together, but not quite. But at least we have a fighting chance now because they're both base 8. Now, remember, log 2 doesn't allow us to bring them together if we have any coefficient other than 1 in front of the logarithm. So now we want to convert this 1/2 factor into the logarithm as an exponent on the argument. So we'll say this is the logarithm of x plus 16 base 8 minus the logarithm of x to the 1/2, which is square root of x, isn't it? Base 8 equal 1. Now we can bring those logarithms together as a single logarithm, and we'll have the logarithm of a fraction, won't we? Where the numerator is the first argument, and the denominator is the second argument, which is equal to square root of 1. X, perfect. And now we can convert our argument, x plus 16 over the square root of x, is equal to 8 to the first power. Now, when we try to solve this equation, then what we would do is multiply both sides by the square root of x. And of course, on the right side, we have an 8 to the first, which is just 8. And when we multiply that by the square root of x, it will look this way, won't it? Now, to continue solving, what we really need to do is to get rid of that square root. And we can accomplish that by squaring both sides, can't we? And when we square this left side, we'll end up with x squared plus 32x. 16 squared, I believe, is 256. I hope so. I'm doing that in my head. You can verify that. When we square the right side, we'll have 8 squared times the square root of x squared, so that's a 64x, isn't it? Now, let's subtract 64x on both sides. We'll have a 32x subtract a 64x. That's going to be minus 32x, isn't it? Plus 256 is equal to 0. And although these are big numbers, I believe we can factor this left side as x minus 16 times x minus 16. And if that's the case, which it is, then we really only have one solution, don't we? X equals 16. Well, we don't need to list it twice. So now we go back and say, okay, if we use 16 for our value of x, all our arguments are going to be positive, and so this is a valid solution, isn't it? Yes, we've got the solution. Well, that was a little different twist. That's kind of fun, wasn't it? I know that's what you think. Well, that's the end of solving logarithmic equations. Next, we're going to talk about solving exponential equations. But that'll be a different lesson.